Let's look at a standard utility maximization problem with the Cobb-Douglas utility function using the Lagrange method. This is a common model in undergraduate courses in microeconomics. So we have a Cobb-Douglas utility function where QA and QB are the quantities we consume of the goods A and B. The weights alpha and 1 minus alpha determine the marginal utilities of the goods. We have a budget constraint where M is the amount of money we have, PA and PB are the prices of the goods A and B. And the equality sign here simply imposes the restriction that the amount of money we spend is equal to the amount of money we have. We also impose some restrictions on the parameters. M, PA, and PB are positive, and alpha is in the open unit interval. This is a standard restriction in the Cobb-Douglas utility function. Let's first look at the graphical representation of this model. So here we have the budget line, which is the blue line, given by this equation, and the green line, which is an indifference curve, also known sometimes as iso-utility curve. To find the solution point, the red point, one of the things we do is that we impose that the slope of the indifference curve is equal to the slope of the budget line at that point. And this means that the ratio of the marginal utilities is equal to the ratio of prices. Here the left-hand side is the slope, or rather the negative of the slope of the budget line, and the left-hand side is the negative of the slope of the indifference curve. That's one condition we need to impose, but it's not enough because there are many indifference curves and all of them are tangent to, all of them have the same slope as the budget line somewhere. So for instance, there's another one right here, another indifference curve, and it has the same slope as the budget line somewhere here. So there's another point here which also satisfies this condition. So in order to isolate the specific point, which is the solution, we also impose that the budget constraint must hold. This is how we find, how we can uniquely identify the point that is the solution. Formally, we can express our problem like this. We maximize by setting QA and QB utility function subject to that the budget constraint holds. The Lagrangian for this problem is equal to the utility function plus the Lagrange multiplier times the budget constraint. The basic idea of the Lagrange method is that we take a constrained optimization problem and transform it into an unconstrained optimization problem, which is much easier to solve. So when we solve the problem of maximizing the Lagrangian, we will, in effect, also solve the problem of maximizing the Cobb-Douglas function subject to the budget constraint. Now, the Lagrangian is concave and continuous in QA and QB. So all we have to do to find the maximum of the Lagrangian is to take the first order conditions, the derivatives with respect to QA and QB, here and here, and set them to 0. That's all. Down here we have the first order conditions set to 0, and we also have the budget constraint because that must also hold. Together, these three equations make up a system in the three variables QA, QB, and lambda. And we can solve that system. To solve the system, we first divide the first equation by the second equation. That gives us this expression here. So here we have on the left-hand side the ratio of the marginal utilities. And on the right-hand side, if we cancel out the lambdas, we get the ratio of the prices. So here we have, in fact, found the condition that the indifference curve and the budget line must have the same slope in the solution point. So one of the two conditions that we need to identify the solution point has been derived. And we see that we can cancel some other things here. We have QA to the power of alpha here and here, so we can cancel those. And QB to the power of minus alpha here and here, so we can cancel those, giving us this expression. Then we move all terms except QB to the right-hand side, giving us this expression. Now we have QB in terms of QA. Then we introduce the third equation in the system, the budget constraint, and we substitute QB in terms of QA into that. So down here, we have the budget constraint, except that I've substituted this expression for QB, which means that the budget constraint now only contains QA, not QB. So we have one equation in one variable. So all you have to do is rearrange and solve for QA. Doing so, we get this expression here. We get QA in terms of only parameters. So we have found the solution for one of our two variables. To find the second variable, QB, we recall the first order condition in terms of QA, and we substitute this expression into that. That's what I've done down here. This is QB, and here we have QA substituted into the expression. And we see immediately that we can cancel out PA and alpha, giving us this expression on the right-hand side. So we have found the solution. We have QA star and QB star. Let's also look at some properties of the solution. First of all, the quantities increase in the budget. So if the budget increases, then QA increases, and the same thing with QB. This makes sense. The more money we have, the more goods we can buy. Secondly, if the price of good A goes up, quantity goes down. This also makes sense. If the price becomes more expensive, we buy less of it. The third point is that the optimal quantity of each good is independent of the price of the other good. So in the expression of QA star, there's no PB. And in the expression of QB star, there's no PA. So if the price of good B changes, nothing happens to my consumption of good A, and vice versa. Finally, the weight alpha determines the fraction of the budget that is spent on good A. One way to see this is to multiply the expression for QA star by PA to get this expression. Now, on the left-hand side here, we have the amount of money that we spend on QA, that is price times quantity. And on the right-hand side, we have simply a fraction of our budget, and the fraction is alpha. What this means is that when PA changes, when it increases, for instance, we reduce QA exactly so much as to make the amount of money that we spend on good A constant. The amount of money we spend does not change.